All right, so just as an FYI, I know some people like to follow the slides like on their phone or on their computer. So the ones that are on the website are a little bit out of date. So this is pointing to my GitLab or GitHub, and should be up to date with these. So yeah, who am I? She mentioned it earlier. I'm a software engineer, probably first and foremost. An adjunct lecturer at CUNY City Tech, teaching Intro to Python, and it's fun to teach because they're forced to laugh at my jokes, so and I fail them if they don't. And so I'm also a PhD student at University of York. I do formal methods and robotics. I'm also, obviously, sort of obvious if I'm coming to a Lambda Days conference, I'm a functional programming enthusiast. So just to be clear, I'm not a game developer. So if you're expecting to leave here, being able to build the next Unreal or Unity or something like that, I'm afraid this is not going to be the talk for you. And I know very little about game graphics, just enough to kind of play around with different stuff I read on the internet. So don't take this as like a definitive guide to doing anything. Yeah. So you're gonna go through my story here. About a year ago, I really decided I wanted to learn sort of the last thing I've always put off learning in software, which is graphics. I've learned everything else. Well, not everything. I've learned a lot of other things, but graphics has always been that weird thing that I know just asymptotically close to zero about. And it's sort of bugged at me. I've had nightmares. I wake up in cold sweats, and I thought it'd be kind of cool to eventually make my own Unreal or my own Unity, and that no one uses. But little did I know that graphics suck. I hate graphics. So when I was a little kid, I did like some Commodore 64 programming, and it was very easy to make a little box spin around the screen and then crash the computer. And so when you look at now, DirectX is Windows only. So I don't have a Windows computer because life is far too short. And Metal is better, but it's Mac only. I do have a Mac, but I don't want to be hamstrung into that. So, a bit of a rant. If anyone here is on a graphics committee, can you just disambiguate this? Because when I go on the forums like Reddit and I say I want to learn OpenGL, people just say, "Oh, learn Vulkan instead." And it's like, yeah. So yeah. And when you try learning Vulkan, it leads to every single decision that led to you trying to learn Vulkan. It's existentially horrifying. So you want to draw a cube in Vulkan? Oh no! Don't start laughing yet. And you try to try this. And then that, and then that, and no, okay? Never again, okay? I learned enough Vulkan to know it is made by Satan, presumably. Okay, so I just kind of threw out most of the mainstream options on there. So you could, of course, I could just use Unity or Unreal. Those are cool. There's nothing wrong with them, but I wanted to make my own stuff because, I'm speaking at a conference. Obviously, I want to make my own stuff. So, they're sort of limited in like what languages you can use and, design decisions and everything, and I don't like being told what to do. And I just prefer open source stuff because, I got to be one of those people that wear like a penguin t-shirt and say, oh, I don't need antivirus. And so, so I could also use an abstraction layer. Abstraction layers will do that, something like that. So what I kind of converged on was WebGL. And WebGL, for those who don't know, but I suspect most people do, it's a JavaScript OpenGL runtime, more or less based on OpenGL ES. An advantage is that it's still pretty low level, so if you want to use like shaders and whatnot, you can still do it. And it's part of the web standards, so it's supported by any device that I'm likely to give a shit about. And also, I can let the Firefox people deal with the Vulkan nightmares that I'm having now. And so, it's a bit slower than using raw OpenGL with C, because you're using JavaScript, or I don't know WASM. I'm not cool enough to do WASM, but it's at least ostensibly kind of confined to JavaScript, but spoilers for coming up ahead here. So I guess to those of you who've never done graphics before, understandable, because I hadn't until a year ago. But basically a shader is a little program that just runs on the GPU, and there's kind of two kinds of shaders. You have fragment shaders, and those kind of are, and this is sort of a reductive thing, but just roll with it. Just pretend I'm right. And so, and then you have, so the fragment shaders kind of determine the colors of the pixels, and the vertex shaders kind of figure out where the vertices are in 2D and 3D space. So this is the WebGL stuff in JavaScript. And so we just do some, we initialize a matrix, we initialize some of our shaders, our matrices, and I can read this to you, but the code should be on GitLab if you want to. But basically, we just kind of initialize the vertices for the cube, we kind of initialize the shaders and can attach the shaders, and then compile the shaders, and that's still, I don't like it, but it's, and then we want to rotate the cube, and that's fine. And here's an example to prove I actually did it. So there we go. That's our cube. Look at that. Isn't that a beautiful thing? I defy you to find something prettier done with OpenGL. Yeah. That's. I'm basically. I'm going to retire my software job and become an artist. But so it is better than Vulkan, at least as a programmer. So if you're stuck doing graphics, I recommend anything but Vulkan, but especially WebGL if performance isn't an issue. But it's still not very fun. It's very long, and I didn't like it. And just spoilers, the ClojureScript code is not much shorter on that. It's roughly, it's a little bit shorter because you can kind of macroize some stuff, but it's not that much shorter. So, okay, so yeah, I determined after doing this, learning how to do this, that I don't want to do graphics anymore. And specifically, I don't want to work with shaders. I don't want to work with all these things. I want to outsource that to someone who has either more free time than me or less love of their life than me. So, so you can use something like P5.js. It's a port of sort of a reimagining of the Java processing library, sort of a little, easy drawing framework on there. And then you can see this is basically the same example I just showed here, but in processing. And that's the entire code, evidently, for that. So yeah, this is better. This is obviously better. Anyone who says otherwise, well, I will fight you afterward. But it's you look at this. Look at that. It's very imperative. You have this stateful thing of like rotate X, and then it's kind of just draw in the background there, and you begin shape, and I'm at a functional conference, man. I don't want to do that. This is bad. So yeah, I liked this better. My life was substantially less horrible when I discovered processing in P5. But we can do better than this. We're functional programmers. So I thought maybe just doing it in ClojureScript might make my life a little better, and it did. So to those of you who have never used ClojureScript, though, if you're at this conference, you probably at least know what it is. But to those who don't, it's sort of a port/implementation of Clojure that compiles to JavaScript. It fully embraces the JS ecosystem, so like a string in ClojureScript is the same as a JavaScript string, not some sort of weird wrapped abstraction of it. And yeah, so one advantage, you can use all the cool Clojure data structures like hash maps and vectors and stuff, but you can also still utilize the vanilla or the nice JavaScript libraries to play with too. So why would I want to use ClojureScript? Oh, and it's Lisp, so I think that's axiomatically cool, but it also, because it's compiled, and it's compiled to a very old, like widely supported version of JavaScript. It runs on the ClojureScript is not going to be the thing that's going to be the problem in your thing as far as compatibility is concerned. It compiles to like ES4 or something. It's really old. So as a result, everything can run it. So I don't have to sit there and worry about like, oh, can I use lambdas or something, or the shorthand function syntax. And the tooling for ClojureScript is actually very good. Pretty nice, actually. And so, but maybe probably the biggest reason is that when you use ClojureScript, the libraries for ClojureScript are usually made for functional programmers and not imperative programmers, because it's a bunch of people like me making these libraries. So, so one of the big pieces of tooling for ClojureScript is called Shadow CLGS. It's pretty cool. It's a sort of a development framework, kind of in a hand-wavy way, similar to NPM, but it uses NPM and it kind of integrates with it. It handles a lot of dependencies in the project structure, and the thing I cared about was automatic hot code reloading. So I can just change something and it will automatically update in the browser, and that's nice. And it does a pretty good job kind of making it easy to call vanilla JavaScript libraries if you want to. So this is a raw port of the P5.js stuff to ClojureScript. And you can see it's basically the same. It's using a lot of mutation, so like the little signs are dereferences from mutable stores and stuff. But it's okay, and it's, I could conceivably make this prettier if I were to do some macros to make it nicer. But so pretty much immediately upon finishing that, I found out, someone did this already for me. So such is life. But so Quill is a ClojureScript wrapper around P5. It's pretty good. It really embraces sort of the functional programming cult, and it gives a very declarative syntax. If anyone here has worked with like OpenSCAD before, if you're in 3D printing enthusiast, no one. It's a very declarative way of working with 3D models instead of having to sit there and pretend LARP as an accountant and do a WebGL. But so this is roughly a port of the same thing using Quill. So you can see this def sketch abstraction here. And there's, this is not everything, because I have like keyboard handlers and stuff here. But in regards to the actual drawing of the cube, you basically have to worry about this draw handler here, which is just that draw state function, and I just draw a box. So, so if we go here, look at that. In that again, I don't want to toot my own horn, but that is potentially the greatest thing ever made by any human. So yeah. So as I said, there's sort of a very declarative syntax to this system here. So you kind of have you kind of just have these little objects, these little raw primitives. In this case, a box, and that's a cube of where each side is 100 of units. And then go away. So with rotation, kind of takes whatever is passed into that state and applies a rotation to it. And you can pass as many boxes as you want into there, and you can make as complicated of a model as you want and kind of just apply this in a very declarative style. It reminded me of SCAD whenever I would make broken things with my 3D printer. All right, so that's kind of the graphical understanding needed to kind of catch up to my understanding of it. So okay. So again, some other history. When I was a child, a wee tot, as they used to call me, no one called me that, but I had a game on my Atari 2600 called Maze Craze. And it was you basically controlled a little blob that was trying to beat another blob to the end of a maze. And sometimes there'd be other little random enemy blobs that would try to stop your blob from getting there. And a bit of an aside, you want to talk about art. Art is all about abstraction, and nothing is more abstracting than pretending that that this is a bunch of cops and robbers and stuff here. Because you can look at it, it's just that looks more like a upside down U to me. But so yeah. So why I'm bringing this up? Why am I bringing up Maze Craze, which no one has done in 40 years? But it's because every time you rebooted the maze, or rebooted the system, it'd be a different maze. So when I was a little kid, I thought, they must be storing millions of levels in here. That's amazing. But it wasn't amazing, because it just generated, it is amazing, but in a different way. It generates the maze randomly every single time you reboot the system. So you get every time you play again, you can get a different maze there. I also thought that was pretty cool. So So this kind of is a segue into level generation. And this is becoming a pretty common thing in modern video games. I think the obvious thing is Minecraft. Every time you reload or you make a new world in Minecraft, it generates it from a seed, a random seed. There's also, if anyone here is interested in indie scenes, there's the Binding of Isaac's pretty fun. Shadow of Doubt's pretty cool. It actually generates a full-on like a detective mystery game on there. It's usually you find clues and stuff, and it's like a randomly generated city. It's pretty neat. But I always thought they were really cool because you can effectively have unlimited gameplay on here. I could conceivably play each one of these games over and over again and never see the same level again. They do eventually become kind of samey after a while, but. So, all right, so the basic, there's too much money has been spent on researching mazes, evidently, because there's so many algorithms for this. But the basic one is this. You just pick a cell to visit. You mark it visited, so like top left corner or something. Find all of its neighbors. For each unvisited neighbor in a random order, break down the adjoining wall, move there, and just recurse. And just do that until every cell has been visited at least once. Or exactly once. So we can do this with Clojure or ClojureScript pretty easily. I'm doing this mutably because I'm not a good person. And so, but basically we just generate sort of a grid, a 2D array or 2D vector here of objects that have a visited flag and the set of broken walls inside there. And this is the actual maze generation algorithm. It might be a little bit scary, but it's not. Basically, all this when does is check to see if the neighbors are legal, if not outside the bounds. And if it is, then check to see if it's been visited. And if it hasn't been, then break down the wall and move the pointer over to that, and just keep doing that until everything's been visited. And so to draw the maze, we got to go back to our Quill thing. So what I did is I just defined a box. And a box is, I'm not great at geometry, but I think it's just 4 lines and maybe some corner pieces there. So what we did is we have a box here, and we just have, we translate the corner pieces. These top ones here are the corner pieces. We just translate them to the width of the box. And then we draw, longer lines for the sides there. And we have these, if the walls are broken, we have a set passed in here. So if the set does not contain up here, then draw the wall on there. And then drawing the maze is actually very simple. It's just looping through a 2D vector and drawing it, translating it the width of your block on each one, width and height of your block, times the depth you've gone. So, all right. So let's say I can show you the example here. WebGL. Oh no. 1 second. I anticipated this. It's 8080. There we go. All right. So. Yeah, so that's basically it. I made a hedge maze, and this is 2D, just using rectangles to do it. So that's pretty cool, and I could of course make this bigger or smaller if I wanted to. It's not hard. Just as a bit of a spoiler, the code power in this is not the code I just showed you because that's recursive, and recursive Stack Overflows if you don't. So I converted it into a gross imperative thing, but I was trying to impress. I'm sorry. Anyway, So yeah, so that's our maze, and I got a little basic keyboard movement here. So this was initially this was 3D, and you can't really see it here, but these are cubes now. But when I was making giant mazes, this was going super slow because I really don't know what I'm doing. And so what I did was I bound something. I bound a key to change it from 3D to 2D, and something that makes Clojure so cool is that I can reuse the core logic to do this, but just define a multi-method to handle for the actual drawing part. So So in my big box method, I just make it a multi-method. And to those of you who have never used multi-methods, multi-methods are just methods or functions, really not a good name because I think of like Java, but where you basically can define which function gets called based on the arguments that are being passed into there. So it's, I made it, no wonder, it's tiny, it's ridiculous. So I just changed it. So you can see that 2D argument being passed in there. So that just dispatches, this is just the rectangle version I showed before. And for the 3D, I did basically the same thing, but passed in the 3D argument. And that draws cubes instead of drawing rectangles. So, and then you just, inside the draw function, I have a key binding that just changes the mode from the state there, and it just passes it in as an argument. Just as an aside, I think multi-methods are pretty cool. And while I would like to say this is like a perk of Clojure, you can do it in pretty much anything. So I got bored one night and not completely sober, and I decided to port this over to Python. So this is, you can steal this if you want, but this is basically just the same thing as Clojure-style multi-methods as a decorator on Python's there. So, and just dispatch based on a Lambda and then register the functions on that. So have at it. But all right, so kind of once I got the maze thing working, I kind of realized level generation is kind of in your heart. It's kind of in your soul, but really it's kind of just any kind of random pattern and adjacency rules. You can kind of use anything at that point. You just kind of define some sort of adjacency rules and patterns there. And sort of what works for you is going to depend largely on the thing you're making. So the lowest hanging fruit, the thing I thought I could do initially was make a Markov chain to do this. And Markov chains are kind of cool, but there's a lot to them that I won't get into. But basically, most of you probably know what a Markov chain is. But basically, it just takes a previous word and then tries to guess the next word based on history being trained on there. And I can show you. I trained this on the opening scene of B movie. Let's see. And then line run b.txt. I wrote this. I should know it. Oh yeah. So there we go. There's a generated thing. To those of you, the hardcore fans of B movies, that's not the opening line. So it's just generated based on the opening line of B movie. So that's just a Markov chain, and the code is, as you saw, it's pretty straightforward. I thought I could do something with levels. I really couldn't, but this kind of does lead to the next one, so I'm going somewhere with this. But, all right, so the people who make these algorithms get bizarrely philosophical. I guess they just feel this is their one chance to shine in life. But so they start modeling these things after quantum physics. So we have a Markov chain. We have, according to, that's the first two lines, some more there. When we get to B, the choice for the next possible word kind of bifurcates. You have the option of potentially be should or of on there. And so these kind of exist in a state of superposition. It's sort of a quantum superposition where they both kind of exist at the same time until we collapse it in some way. So say we choose the of path there. So we collapsed that way. And so we've chosen the of. And then we maybe choose course, and that closes, that trashes aviation. And so this is effectively a lazy data structure at that point. But yeah, so limitations of Markov chains is that they're cool, but they're kind of limiting. They're generally one-dimensional. And it's kind of, I couldn't really figure out a way to do it for anything but generating funny text. So it's just threw it away. But there's sort of an abstraction. Software is all about abstraction. And sort of an abstraction of a Markov chain called a wave function collapse, which has an unjustifiably cool name. But it's sort of, you can kind of think of it as a sort of an multi-dimensional Markov chain. It can kind of do lots of different stuff, but you can kind of use it for n-dimensional stuff there. It's been used to generate like poetry and music and it's levels, obviously. But the basic algorithm is you just sort of have some sort of adjacency rules either provided from some sample data or you just define them yourself. And then you kind of assume in a grid or an n-dimensional grid that all of these adjacency rules and all these tiles in the states that they're allowed to be exist simultaneously in some sort of quantum superposition. I'm using quantum in a hand-wavy way, but so does the paper that published this. So, and then you collapse that wave by picking the next one of the possible positions on there, and then kind of reevaluate the allowed things on there, and you repeat until you have a grid that you're happy with. So, sort of a visual example here. So, imagine we have a 2D grid, and for each tile, there's 10 possible states starting out there. And so, these 10 represent the number of states that are allowed, the number of tiles these could be in a tile map. So, say we choose one. We collapse the wave of the first tile there. So, you notice that the surrounding ones, might have adjacency rules for red. There might be adjacency rules for red tiles here that limit how much stuff there. And then the adjacents to the adjacent tiles might have limiting and go from there. So we can collapse another one that's purple, and then you see it collapsed some other waves there. You can see the numbers change in sort. And then we kind of keep doing that, and then eventually we have a tile map on there. So typically you define the rules of adjacency by some kind of sample input, like people commonly use pictures, like with a sprite drawing software. It's kind of like a Markov chain, and I have my own version of this, but it didn't work. Well, let me phrase. It did work, and then it didn't work this morning. So let's see here. So if we go to our WFC. Okay, so our sample input. Let's just open this. We go to our sample input. So our sample input would be this flower. Oh, isn't that pretty? So we go. If you could see it, you'd see. Isn't that gorgeous? I didn't draw this. This is actually something in the wave function collapse paper. So that's a little pixel flower on there, right? So let's see. If we do a line. All right. So we'll draw a 256 by 256 grid. The tiles are three pixels wide on there. And we're outputting it to out4. So once it finishes processing. I didn't say I wrote good code. It just exists. The good code exists in superposition somewhere else. But eventually, come on. You're embarrassing me here. There we go. So, out. So you can see. Isn't that cool? So it generated this based on that seed input of the flowers there, because it just looks at the adjacent, it deduces what adjacency rules it can based on the tiles there, and then just kind of, power of RNG on there. So I thought that was pretty cool when I first saw it, because you can actually look at the code. I think I have it open, actually. The code to do this, it's not that bad. Like, this is the entire algorithm for it. It's like 150. I mean, I'm not going to walk you through each line. You can read it yourself. There are links. There are links in the slides. But you can see the actual generation for it is actually pretty cheap on there. So yeah. Further reading on this. If you actually want to make Minecraft, they use something called Perlin noise. And Perlin noise is kind of looks like TV static from old cathode ray tube TVs. So Minecraft uses like a modified, Minecraft probably uses like a dozen things now. Minecraft initially used Perlin noise, but sort of a gradient noise thing, so it's not just like choosing a RNG for each pixel on there. There's a pretty good blog post about wave function collapse that's worth checking out, and it's you can download the slides and look at that. That's it. I don't do social media, So if anyone here wants to email me, feel free to do so. But I don't have Twitter or anything like that. So, and that's it.
We still have some time, so do you have any questions? No hands in the air? Oh, there's the first hand.
Do you know any other use cases for a wave function collapse other than generating graphics? Like some practical stuff.
Well, what is practical? I mean, practical. Fun. Okay, so yeah, so effectively anything that can be modeled as sort of an infinite thing. So I think Shadow of Doubt might be using wave function collapse. I have to get in contact with the author, but in regards to like fun things, I can show you the. If we go to wave function collapse algorithm, yeah, this blog post here. People have used it to generate like poetry on here. So what I gave you was a reductive version because what I showed you, if you just go propagate straight from like one corner, you occasionally get things where the 0 states are possible. And so typically what you do is you find you collapse the one with the fewest number of possible states first and kind of go from there. So, but that's why it goes in a different order on that. But yeah, there's that. There's people have generated bad music and stuff. You know, generate towns. We can actually have that here. What's I think it's city. Yeah, that's it. So this is the template for a city here, and you can't really see that, but so this is like a map of a city here, and once this finishes running, if it ever finishes running. But yeah, you can see. So it's not just you can use it for tile sets. You can use it for kind of anything that could be procedurally generated. And before you ask, I did look into ChatGPT to do this. It didn't seem to care that the levels were impossible that was generating. So, but yeah, so we can look here. You see, it's kind of following the same adjacency patterns for the city there, and it's that. But yeah, anything that can kind of has some sort of next or adjacent pattern to it, you can kind of play with. I think there's a question there.
Okay.
Sorry, thanks. Great talk. Is there a way that you can guarantee that your adjacency rules will always result in usable maps? Like, it kind of gets stuck in a position where there's nothing that fits inside a space?
I think no and yes in that order. I don't think there's any way to guarantee it as far as I'm aware. There might be, but I couldn't find any research on that. It just seems like you can almost always avoid that if you just choose the one that has the fewest number of possible states next. But to answer your question, I think the answer is you can still technically get into unsolvable states. Then they say start over, basically, on that. Oh,
Do you want Mike?
One typical strategy for that is that you use one form of generation to generate the successful path effectively, and then you use a second pass to build everything around that.
Thank you.
Do we have any more questions? So I just have to keep waiting and the questions will appear.
What can you do when there are requirements for a level which cannot be described by adjacency rules? For example, when you generate a maze and you want to have an entrance at one point, for example, top left corner, and you want the exit to be at the bottom right corner. So you basically, can you deal with requirements like that?
Well, in regards to the maze thing, there actually is no. We can look at it, but basically, if I can Where the hell is this? How do I keep losing this? There we go. This will actually, you can just punch a hole, in this particular case, you can just punch a hole basically on any of the walls, and that'll still be, you'll still be able to get there. There's no dead ends in this particular maze algorithm. With other ones, it depends on which algorithm you're using on that. I can't answer that in any kind of a general case. In wave function collapse, I think you'd have to kind of define those first, and then, as they said, kind of define the thing around that, either using another algorithm or kind of branching off from the safe paths first.
Anyone else would like to ask a question? That's okay.
Maybe I missed it, but how are the adjacency rules extracted from the picture, like the flower picture? So is it like each grid cell is like, if I see a yellow and a blue one, or does it take frequencies, or does it look like some bigger patterns?
It does take frequencies. It doesn't work in very high noise images typically. So these are, obviously this is very high contrast. So it's very easy to kind of just go by three by three blocks on there, and then see, kind of divide these up into chunks, and then see what's been adjacent based on that. And then it is a frequency thing on there. So the more frequent stuff has higher weight based on that.
So it looks at chunks, basically, not like single cells, and it doesn't count cell by cell, but by 3 by 3 chunks or something like this, right?
Yes.
Okay, thanks.
You have a question?
You can also use tiles, for example. It's often used in like game development, and you just look at the tiles next to each other, and that's going to do it. Also, the size of the chunk is also customizable as far as
yeah. Even in my code here, I didn't mention that the 3 here is, I make that bigger so you can see it, but this is the size of the tile, and then this is the actual size of the output, and that's the name of the file there. So.
Any more questions? Okay, looks like that's it. Thank you very much.
Yep.